hypothesis testing. Okay, give you that. It's not guessing. Okay, please, not guessing. It's not guessing. So I'm just trying to think about the good example. Let's say we have a kind of we are selling a bag of candies. Let's say we're selling a bag of candies, and then we advertise what the average of the candy. Okay, a bag of candy is 10 kilos too many. Let's say 1 kilo is already a lot. Okay, 1 kilo. So the mu is 1 kilos. Okay, mu is 1 kilos. And then someone go home and then say, weigh it and find the mu is, well, 1 kilo is still quite shocking. So 500 grams. Okay, then calculate that the X bar, let's say that's X bar, no, not sample, like the mu. Still use X mu, let's say still use mu. Mu for what they buy is 400, well 98 is too much difference. Well, it's okay, it doesn't matter. And then this person wants to make the announcement, okay. Your mu for this candy is no longer 500 grams. Okay? Well, because I waited and I find it's less than 500, I say, well, your mu is not necessarily 500 now. I think it's less than 500.
Right. So, if you buy a lorry bag,
yeah,
and then you weigh it, that's not going to be that.
No, it's just because of my experiment. That's just an example. That's just an example, like mu is like what I have, because I observe it. I observe that. Well, it's not really the actual thing. I'm just doing an example here. I'm just telling you a story. It's just treat that as a story. Okay, treat it as a story. I say like I have an average weight of 500. Okay, and then someone buy it, and then I weighed it, and I find that's a 490, and I'm not happy about this fact. And I think you are not giving a correct advertisement here. And I said, I will make an announcement that is less than 500 now. Well, I don't know how much is less. I will say it's less than 500 now. So I make an announcement that your mu is less than 500. Okay? But is that really true? Say, you have one observation and you find that's a 480, or according to your sample, let's say I buy 10 candies and I find average. Well, let's say not one. Okay, if you say that worries you, I'm not saying one. I buy 10 candies, 10 bags, and then average them. I find it's a 490. Okay, on average. I say, okay, the mu is no longer 500. I say it's less than 500. But you know that we have standard deviation as well. I can still set up the mean at 500 and it still can achieve 490, right? It still can achieve 490. It depends on what is your variance. It's still a chance that you can achieve 490. Now, then the question comes, is that because the variance between the data to data, like, it's just bad luck? The mean is still as 500, but you just get the bag, which is like quite far away. That's your bad luck. Okay, or if it's really that the value go down, like the mu go down. So that's the hypothesis testing. That's like, okay, then let's take that into investigation. So what we have originally, what we advertised originally is called H0. The H0 says, oh, we have a mean of 500 grams. Then your H1 is mu less than 500 grams. Okay, that is your hypothesis testing. Okay, that is your hypothesis testing. So it's called the Null Hypothesis. It's called the H0. Since the sample is drawn from a population, okay, so from population is the true. Actually, it's called the true mean, which has the same mean as before, and that any difference we observed. Okay, any difference we observe, for example, this 490 thing, any difference we observe is explains as sample to sample variation. Okay, it's just your bad luck. You just get all the ones with a smaller weight. Okay, that's variance between sample to sample. But your mu still can be 500. And the alternative hypothesis is talking about H1. Says that while there will always be some sampling variability, the amount of variation is so much that is more likely that the sample has been drawn from a population with a mean is not the same as that of the original population. Okay, so basically what the sentence talking about is the variation is too much. Okay, it's, for example, I have 500. If I have 500 new, and then the probability of getting less than 490 is 95%. It's quite high, or even 99%. It's quite high. It's very easy to get that. So we are not rejecting the first one. But say if the probability less than 490% is really a low chance, it's only 1%. Well, I'm very likely to reject the H0 because it's so hard on your theory, in your population theory, that to get something less than 490. Okay? In your original distribution, you give me a mu, you give me a standard deviation. And I find, oh, okay, the less than 490 is actually really low probability. Well, I don't think it's a sample variation thing. I think it's really something wrong with the mean. The mean is different for my sample, okay, for the thing I collect. So then I will reject H0. Okay, I will reject H0, reject the null hypothesis, okay? One thing needs to be aware here is you never accept hypothesis 1. You only say you reject, okay? I only 2 results, reject or do not reject. The H1 is somehow said is your guessing. I never say I will accept it. I never say I accept H1. Okay, that's like a statistics thing. In uni, you have the same thing. You won't say you accept it. It's not choosing between 2. Do you understand? You're not choosing between 2. You only test about the reasonable, whether it's reasonable for your guessing. I only say one thing is I will accept H0. I still do not reject H0. The second is I do reject H0. Everything your conclusion made is to 0, H0. It's just a rule, okay? You never say, okay? The mathematicians never say you accept H1. You only say you reject or not reject. You do reject, you do not reject H0. Okay? Nothing to do with H1. You never say anything about H1 in your conclusion. You only say you reject H0 or you do not reject H0. Okay? That's the 2 conclusions we have. Okay. So, too tired. So, example 1. Okay, give the non and alternative hypothesis for the following situation. Okay, have to think about that. A swimmer has been swimming 50 meters in 32 seconds on average. He has been following a new training program, which he hopes will decrease the time it takes him to swim 50 meters. He is going to time himself in the next 20 swims. Okay, 15 meters in 32 seconds on average. So your H0 is from all your stats before is your mu equals to 32. Okay, your mu equals to 32. And then what you want for H1? Okay, tell me what you want for your H1. So what? Less than 32. That's H1 is mu less than 32. That's the 2 hypothesis testing you have. And he hopes he will do that. And he will test next 20. Okay, next 20 and find average. Well, we're not talking about any calculation here. We just list the hypothesis test first. Okay. B. In the report, it was stated that the average age of all hospital patients was 53 years. A newspaper believes that this is an underestimate. Okay, so what my H0 will be? No. What is my H0? What 53? You're not going to write 53. Mu equals to 53. Okay, what my H1 will be? Mu larger than 53. That's what others believe. Okay, I will test in between those two. Oh. Should learn English if you do not underestimate. And why the p jump up? Okay, it's the p-value. It's called the p-value. Okay, I will ask you why you will suspect the mu is not the original one. Is that because you observe something? You have observed something, then you make this assumption, right? So the observed value is important. Okay, the observed value is important. So let's have a look at the next question. Right? Like you observe something, like say the bag of candy, I observed the average is 490, and then I start to suspect that, well, it's not 500 anymore. So it's because of the observation values, then I start to think about, well, is that true or not? Okay, the p-value is the probability of the observing a value of the sample statistics as extreme or as more extreme than the one observed, assuming that the Null hypothesis test is true. Okay, don't understand, that's fine. But what I'm going to talk about is, okay, if this hypothesis test, mu equals to 100, and I assume mu is greater than 100. Why I'm assuming that? Because of a size of 100, I find my x bar is 103.6. Okay, because I observe something and I find it's greater than 100, now I start to suspect, is that true? I have a larger than 100 mu. Okay, like it's because of this observed value that I start to suspect. Okay, what is the p-value? Is the more extreme value. So what I observe is 103.6, right? Now I assume that mu is greater than 100, so the sign will follow you H1 hypothesis testing. So what I want to find is probability x bar greater or equal to that is like the extreme or even more extreme value compared to the observed one. I'm finding the probability on the distribution that this. Okay? That makes sense? Like more extreme value. So the sign will follow the H1 sign. It's not like you guessing it. Okay, follow the H1 sign. So I observe it's 103.6, blah, 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 blah. Then I need to think about any value on the right-hand side of that.
So it's like the probability that H1 is
Not H1, it's the mu. It's the sample mean. What I assume here, what is H1 is that I assume sample mean is greater, the expected value for the sample mean is greater than 100. And then now what is the p-value? We are looking for the p-value. How the p-value can be calculated is by finding the sample mean greater than 103.6 or equals to that, assuming that the H0 is true. P-value must be assuming the H0 is true. Okay, you are not using H2. H1 thing, you must assume H0 is true. So what x your distribution follows? Your distribution of x is x bar is a normal distribution. X bar is always a normal distribution with the mu 100, comma standard deviation over square root of 100 because it's a sample size of 100. And x bar never change. Doesn't matter if by this hypothesis testing or not. It's always a normal distribution. With mu is given, that's 100, and standard deviation. I don't know the standard deviation in this question, but over square root 100. Okay. Now the distribution of the sample mean. Well, x is. Oh, okay, it's correct. Well, why all jump up? Well, I changed it a couple of times already. Okay, if x is a normal distributed random variable with mean mu and standard deviation sigma, then the distribution of the sample mean x bar will also be normal. Well, this is given already. Okay, last chapter. And with mean expected x bar is mu and standard deviation is sigma over square root n. N is the sample size. So what it's basically talking about is x bar is normally distributed with mu and standard deviation over square root n squared. That's the notation. Sorry, that's the notation. Well, this is given. Okay, last chapter, chapter 15. You just like use this fact again. Let's have a look at example 2. Example 2 says, for extensive recourse, it is known that the required duration of treatment for a disease by a standard technique has a mean of 15 days and standard deviation 3. Okay. Extensive recourse is known the required duration. Let x be the duration. Okay, let x be the duration of treatment of a disease. Okay, I'm not going to write it. So x will be normal distribution with a mean of 15 days and standard deviation 3 days. So x is given by that. It is claimed that a new technique is going to reduce the treatment time. Okay, reduce this treatment time. To test this claim, the new therapy is tried on 7 patients. So n is 70 patients. Is on 70. Write down the null and alternative hypothesis for this test. So H0 is claimed that mu is 15. H1 is talking about mu is less than 15, right? Okay, B. Then that's x bar. Okay. X bar is given by normal distribution with a 15 and the 3 over square root 70 squared. Yeah, that's what's the sample mean. Okay, sample mean distribution. Sample mean is a normal distribution with 15 and standard deviation 3 over square root 70. And if the sample mean is 14.6 days, determine the p-value. Okay, what's the p-value? The p-value will be even extreme value compared to observed one. So it's the x bar less than 14.6 days. Well, it doesn't really matter. It's a continuous random variable. Well, you can put equals as well. Well, because I'm follow this sign here, I say it's less than that. It's absolutely smaller than that. Well, it doesn't matter. It's a continuous random variable. The value will be the same. So 14.6 days. Okay. Mu is 15. So menu 552. Next infinity to 14.6 days. Okay. We use the original mu because I'm testing whether it's true or not. That's mu and standard deviation is, what's the standard deviation? 3 divided by square root of 70. That probability is 0.1323. That is the p-value, okay, 0.1323. Okay, so the next thing we talk about is why it is important to talk about the p-value. What do you think the p-value represents?
The possibility of learning value of the
Why? I'm not asking you to read the definition for me. Okay, so Let's sketch on this graph, okay? Let's sketch the distribution for x bar. It's a normal distribution. With mu 15. And then it's observed a value. Well, standard deviation is that. Well, let's calculate what standard deviation is. 3 divided by 17. Ah. 3 divided by 17. So 0.35. That I use 15 subtract that. It's 14.6 and it's even 14. What I observed, 14.6. Okay, it's one standard deviation is here, and it's a little bit smaller than one standard deviation. Okay, I observe a value here. Okay, I observe a value here. The area I'm finding is this. That's the p-value. That's 0.1323. Do you think that is easy to get? Do you think it's easy to get a value that is less than 14.6? Kind of, alright, it's 13%. Okay, it's 13%. It's a large probability. Okay, it's a large probability. So what's the point is, what basically you think about is that easy to get that value? Okay, is that easy to get the value? If it's easy, well, if it's easy on this distribution, if it's that easy to get this value, then my mu has no problem. Okay, well, it's not strange that you get a value like that because it's easy to get those values. Does that make sense? But let's say if that area is only 0.0001, do you think that's a strange thing? It will be hard to get that mu, okay, you observed, which means there's something is strange. So you should reject it then. That's the point for p-value. Okay, is that kind of make sense? What you need to think about is, okay, the extreme value compared to observed value. Is that an easy thing to get? If it's an easy thing to get, well, if it's easy, nothing strange, you get that value. So it's just sample variations. Well, you don't need to worry about it. Our mu is all good. But if that area is very small, if it's small enough, I would say it's too small to get, too hard to get. Oh, now you get that. You reject. I'll talk about that next. Okay. So what percentage will be a rejected percentage? That depends on the question gives you. Okay, you don't know that. Normally is a 5% reject value. Because normally it's a 5% reject value. Change page. What's wrong? Where's that? You must use sample size. If it's x bar, you must use sample size. The 3 is the x distribution. It's not the sample means distribution. So sample mean, if it's a sample mean, it must connect with n. Okay, sample mean, you need to know how many samples you take, and then vary from sample to sample, the standard deviation will be different. As I said, the larger the sample you take, the less variation you have, the less error you have. So you have a lower standard deviation. So that must connect with your sample size. Okay. Normally, your p-value less than 0.5, less than 5%, we said is good evidence to reject the first hypothesis. Okay, if it's less than 5%. But in some case, well, let's say greater than 5% is definitely insufficient evidence against H0. If it's less than 5.5%, it's good evidence against that. While in some extreme case, the scientist said, well, I just want a really small value. Then if it's 1%, I would say it's strong evidence. If it's less than 0.1%, it's called very strong evidence. But you're not guessing values, okay? The question will tell you in what percentage you reject your values. Okay, in what percentage you reject your values. Okay, it's called the statistical significance. The significance level of a test, alpha, is the condition for rejecting the null hypothesis. So you will say the significant level is 5%, which means when your p-value less than 5%, you can reject H0. Okay? When it's less than 5%, you can reject H0. If the p-value is less than alpha, the alpha is like the percentage or 0.05, then we reject the null hypothesis in the favor of the alternative hypothesis. If the p-value greater than A, then we do not reject the hypothesis. Okay? We reject the null hypothesis in favor of the alternative hypothesis. We didn't say we accept it. I just say it's more likely to be that. Okay, it's more likely to be that. The most common value we use is 5%. Okay, the most there's still 1% and 0.1% also be used in some cases. It depends on what it's asking. Normally it's 5%. Okay, normally it's 5%. Okay, z-test. So what is called a z-test? Is the normal. Okay, it's connected with the normal. The hypothesis test for a mean of a sample drawn from a normal distribution population, which non-standard deviation, which with non-standard deviation is called a z-test. Okay, so don't worry about the z-test. You will learn t-test, you will learn chi-square test in the uni. There's more types of tests, but the z-test is combined with normal. Don't really need to know much about the z-test. It's just normal distribution. And then you talk about the hypothesis test. It's called a z-test. Okay, let's just do one last example here. The average weekly rental for a one-bedroom apartment in a certain state is normally distributed with, well, let's let X be the rental price weekly. So X is normally distributed with a mean of 320, a standard deviation of 120. Well, standard deviation is quite large. Okay, to test whether rents have recently increased, a real estate agent takes a random sample of 15, okay, n equals to 15, such properties, and determines the average rent to be 340. Okay, to be like the average is 340. Write down the null hypothesis and alternative hypothesis for the test. But first of all, I'll say my x bar. Well, I'll write my max bar later. So that's according to what we have. Then write down the non and alternative hypothesis. So H0 such that mean equals to 320. How about H1? Yeah, must be greater than 320. It's not equal. You can never have like equal, like it's always greater. Okay, greater. B. Determine the p-value for this test. First of all, let's say what's x bar? 320. We still assume H0 is correct this time. Okay, 320 and square root of 50 and squared. That's the notation. That's probability that x bar is greater than what? 340. Okay, it's not 320. It's 340. It's the observed value. If you said greater than 320, that's 50%. We never reject it. Okay, it must be greater than the observed value. You want to see, is that easy to get observed value? Okay, the observed value. So that equals to 340 40 to infinity. Mu 320. And standard deviation is 120. The 120 is the standard deviation, right? It's the standard deviation before. It's not the variance, right? Over square root of 50. 200. 120. Okay, 20. Okay. 0.119. 0.12, let's see. Okay, 0.12. And do you think it's good enough to reject it?
No. How come in this question is you given me
Oh, no, you don't really need to write that. Well, it's alright you write that. It's just, this is telling you, when we calculate the probability, we use the original, like the true population mu. We are not using the, currently we find what we find. We use the true mu to calculate. Do you think that's enough evidence to reject it? Like the C, for C. It's greater than 5%, so C, 12% is greater than 5%. Do not reject. H0. Okay, we do not reject H0. So it must be within. It must within 5%. Then we reject. Well, 12%. Have a think. It's so easy to get. Okay, it's so large possibilities to get it. So we do not reject it. Okay. Okay. I may just write that into 4 decimals, but it doesn't matter. It's easy to pick it up.